This MEB video is a combustion practice problem. The problem statement is short and sweet. Propane is burned completely with excess oxygen. The product gas contains 24.8% CO2, 6.12% CO, 40.8% H2O, and 28.6% O2. What is the percent excess of O2 fed? Once again, start off the same way we always do with drawing a process flow diagram. So pause the video and draw your own here. Here's my process flow diagram. I wanted to note the following few things. First, that I drew my fuel and my excess oxygen streams in separate incoming streams. So again, I don't have to do that. You could feed them both together. I just think it keeps it much easier to keep track of if you have them in different streams. And also, I mean, a combustion reaction is probably going to be separate feeds anyway. So in an engine, for example, you feed fuel and you mix it with air in the carburetor, I guess before that happens, before the combustion reaction occurs. But you just think about these things being fed in different quantities anyway. But this is going to make it a lot easier to calculate my excess O2 at the end. Another thing I wanted to point out is that I had to look up what, I didn't have to look it up, but you might have had to look up what the chemical formula for propane is. Once again, I recommend that all chemical engineers memorize what the first 10 hydrocarbons are. Propane is C3H8. And I've just copied exactly what the problem statement has given me in terms of the percentages. I'm assuming that these are mole percentages. Once again, it doesn't say specifically, but to make my life easier, I'm going to go with the thing that is easier to assume. So because it's a chemical reaction, I need to balance moles. And I would assume that if it were weight percent, it would have explicitly said this was weight percent. And then also I have a flow rate of product gas N3. So I want to figure out what is the percent excess O2 fed. And in order to do that, I'm going to need to figure out what N2 is and what N1 is. So I'm going to have to calculate what the theoretical O2 is by knowing how much fuel I have, and then calculating how much N2 is in excess. So the next thing I might have to do is to balance my chemical reaction. And as I said before, that any chemical reaction with combustion is going to be the fuel. Let's write it over here. The fuel reacting with O2 to make carbon dioxide and water. Now, in the previous video, I said I made a note about this word completely, and it could have two alternate meanings. And with context clues, you can figure out what it's supposed to be. So one of the meanings of completely is not possible, and that is because I have CO2 in the product. So that means incomplete combustion is occurring. And then another hint is that I don't have C3H8 in the outlet stream. So that since there is no C3H8, I'm going to interpret this as 100% fractional conversion of the fuel. Okay, let's get to the reaction. First, I want to tell you again what not to do. So this would not be a proper balanced chemical reaction to write. You should not do this, right? I'm writing out the balanced reaction, assuming that carbon dioxide and carbon monoxide are both in the products, and H2O. So notice that this is a balanced reaction, as I just said. So I have 6 carbons on the left, 6 carbons on the right. I have 16 hydrogens on the left, 16 hydrogens on the right. And I have 17 halves O2, or 17 oxygens on the left, and 3 times 2 plus 3 times 2 plus 8 is, oh, wait a second. Oh, I see my mistake. This is CO, not CO2. 3 times 2 is 6, plus 3 is 9, plus 8 is 17. So this is a balanced chemical reaction, but once again, do not write your reaction this way. And the reason why is because this reaction implies that carbon dioxide and carbon monoxide are formed in the same quantities, in the same amounts. And that's not true. Typically, you're going to have more complete combustion occurring than incomplete combustion. And you can see this because in the product gas, I don't have a 1-to-1 ratio of CO2 and CO. I have a 4-to-1 ratio closer like. So once again, this is not the correct chemical reaction. I need to write my chemical reactions in separate parts. So I'm going to write my complete combustion first, C3H8 plus O2 is going to CO2 plus H2O. And let's balance this. I need 3 carbons on the right. I need 8 hydrogens on the right as well. 3 times 2 is 6, plus 4 is 10, meaning I have 5 O2 in the complete combustion. And I'm going to have incomplete combustion as well. C3H8 plus O2 is going to CO plus H2O. 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens. 3 plus 4 is 7, 7 halves O2. So this is my reaction network. Okay, the other thing I wanted to point out is that if you tried to add these up, these sum to like 100.3, I think is what I got. Don't be alarmed by that. That's within rounding error. So I'm not sure where I got this problem from. I think I got it from the book, but just the fact that they don't add up to exactly 100 is not a cause for concern. So in real life, you'd probably get these percentages from a gas chromatograph or something, and there'd be experimental error, and not closing to within 0.3 is not a big problem. All right, so let's do a degree of freedom analysis. First of all, we have a reactive process here, so we have to figure out whether or not we want to do the atomic method or the extent of reaction method. And I think I showed the extent of reaction method last time, so I'm going to showcase the atomic method here. So let's do our degree of freedom for atomic. Once again, your method should not affect your final answer. So I encourage you to try out the other method and verify that you get the same thing in the end. So let's do the atomic degrees of freedom. And for the atomic method, I'm ignoring the chemical reaction, so I don't have to take that into play. So I've got 1, 2, and 3 unknowns for the flow rates. 3 unknowns. And I have, let's see, carbon, hydrogen, oxygen are my 3 atoms, correct? 3 unknowns minus 3 atomic balances. And then also, in this problem, I think I need to set a basis because I have not been assigned a basis yet. So I actually have -1 degrees of freedom here. So I'm not going to let that deter me. I think that, again, if you have -1 degrees of freedom, it's either redundant information or it's contradictory. So let's just do the balances and we'll see if they work out in the end. And if they do, then that means that we have redundant information. All right, now I've said that it is always advantageous for you to assign the basis to a stream in which you know what the composition is. So for that reason, I'm going to assign N3 as my basis. And that is going to be equal to 100 moles per minute. Okay, again, because I know what the composition is, that should make it easy to figure out what my moles are. All right, so 3 atomic balances. Let's do a carbon balance. How much carbon do I have coming in? I've got N1 moles of fuel times 3 moles of carbon per mole of fuel coming in. And coming out, I've got 24.8. This is why assigning a number of 100 is useful here, because it just makes the conversion from percent to moles really easy. 24.8 times 1. Again, you don't have to write the 1. I'm just doing it so that it's very clear what I'm doing. 6.12 times 1. And that's it. My hydrogen balance is N1 times 8 is equal to 40.8 times 2. And my O2 balance. Oh, one more thing I forgot to mention is that I said to always keep in mind that there's nitrogen here. And I said that 99% of the time combustion problems are with air. This is that 1% where it's excess oxygen. So I don't have to worry about nitrogen here, but whenever you see combustion, an alarm bell should always be going off in your mind to always include nitrogen. So I don't have to include it here, but in the future for problems, you will have to. And nitrogen balance are oftentimes easy because it's not reacting, it's just always in is equal to out. Even if you don't do the atomic method, even if you do the extent of reaction method. Okay, O2 is going to be N2 times 2 is equal to 24.8 times 2 plus 6.12 times 1 plus 40.8 times 1 plus 28.6 times 2. All right, and it looks like I have a couple of reactions that are not going to be super difficult to solve. So solving either one of the first two equations gets me that N1 is equal to 10.2 or 10.3. So I did get slightly different things, but I'm not going to be worried about rounding mistakes, which it seems like that is. So in this case, information is redundant, 10.2 moles per minute, and info redundant. So again, that's one of the possibilities when you have -1 degrees of freedom. It actually means that I didn't have to specify everything that was in the outlet stream, but the problem gave me more information than I needed to solve, and it worked out that it works out in the end. Okay, now let me caution you again of what not to do. So when you do an atomic balance, even though you are ignoring the reaction, what you should not do, I'm gonna write this in red, so I see this mistake all the time, do not do an overall mole balance. Do not do this. Do not say that N1 plus N2 is equal to N3, like we did for a non-reactive balance. And ask yourself why I shouldn't do that. And that is because for a chemical reaction, moles are not conserved. Moles are not conserved in a chemical reaction. So students mess this up every semester. Please do not be one of them in a reaction. So just look at the chemical reaction, right? So on the left-hand side for complete combustion, I have 6 moles on the left, making 7 moles on the right. So molecules are recombining. They do not have to form the same number of moles. I don't have conservation of moles for the incomplete combustion either. And in general, I will not have moles being conserved. Now, sometimes I will say that you can get clever, and if you need another piece of information, if moles are conserved in your chemical reaction, you may be able to say it. But in general, do not write your overall mole balance. You will not be able to solve it, and it will not be correct. So in other words, if I solve for N2, given what my basis of N3 was and my N1, I'm going to get a different answer than I would by solving N2. So I stopped short of that, by the way. Let me work this out on my calculator. So I got that N2 was 76.9 moles per minute. So once again, notice that 76.9 plus 10.2 does not equal 100. So that is not a valid way to account for it. Now, I've solved for all the variables in my process flow diagram, but I have not solved what the problem wanted me to solve, which is what is the percent of O2 fed, percent excess O2 fed. So I have to work out what is my theoretical O2. So remember that theoretical O2 is the amount of O2 that I need to combust my fuel completely. So I need to take 10.2 moles of fuel per minute and multiply that by the ratio of the stoichiometric coefficients. So once again, when I calculate theoretical O2, I'm not taking into account the incomplete combustion, and I'm also assuming, even though that is the case for the problem, that all the propane is going to combust. So I need to multiply this by 5 moles of O2 per 1 mole of C3H8. Don't forget to divide by the ratio. I sometimes forget to do this myself because I oftentimes write my chemical reactions such that the first stoichiometric coefficient is 1. But you have to keep in mind that if I multiplied the whole thing by 2, it would be per 2 moles of propane. And then obviously it'd be 10 moles of O2, so it would work out the same way. My point is just never forget about the stoichiometric coefficient of your reactant. So this is what? 51, I think. 10.2 times 5 is 51 moles per minute O2 theoretical. All right, so to work out excess, and I can either go to my book or just rationalize. The theoretical is difficult to spell, I guess. Theoretical. Okay, so the equation for excess reactant is fed minus theoretical over theoretical. And this can also be stoichiometric. So theoretical and stoichiometric can mean the same thing. So how much O2 did I actually fed? I fed 76.9 minus 51, all divided by 51. And doing that calculation gives me, I have 50.8% excess O2. So hopefully you enjoyed this practice problem. Helps get you used to doing combustion reactions. Thanks for watching. See you in the next video.